All right. Good evening, everyone. This is Celso Batalha, Shoten, Astronomy 10 Online. There are two things I would like to remind you about it. Not to remind, in fact, is to one is to remind, and the other one is a new information. The reminder is this Wednesday we have a talk of Dr. Nelly Batalha on um, exoplanets, and this talk is going to be in Foothill. Sorry. It's gonna be that's my daughter. It's gonna be in Foothill College, and it starts at 7 o'clock. But I would like you to try to get there at 6:45 if you guys are tempted to go. The reason is there is a big line of cars, and then you park, and then you have to walk few ranges of stairs all the way to the auditorium. I mean, there is no way you can get lost because you have a bunch of people going to the same place, so just follow the crowd. But there is a line of cars. So if you are planning on arriving there at 7 o'clock and just park and then you are in the auditorium, forget about it. You gotta, in order to see me, make sure you get there by 6:30ish, 6:35. At 6:45, I will be at the door, and then by 5 minutes before 7, I will be entering, and I will be in the auditorium. You don't need to stay there all the way to 9 o'clock, but you need to attend at least 1 hour of the conference that goes from 7 to 8. And then from 8 to 9, usually they open for discussions and questions, and the questions are very good. So if you are on the mood and on the momentum, just stay over and attend the conference. So to get the extra credit, as I said, you have to then upload a text with your understanding of the main topics discussed in this conference. It's pretty much informative. It's not a lot of a technical work, although the communication is technical, and it gives you some very upfront information of what's going on in the exoplanet front line. And it's an exciting area of research, and there's lots of investments made for it. A few other programs are on the queue line to be launched in the next few years, and the conferences will be talking about all of those programs. So it's a great thing. It's a nice way to complement what we study in astronomy, and I invite you to go and you get extra credit. Any question? Okay. We are kind of advancing now in the realm of stars. So we studied a couple of weeks ago properties of stars, and then we learned that light is the mechanism by which, not mechanism, but is the carrier by which we collect information about celestial objects without going there. So as we observe stars and galaxies and quasars and clusters of galaxies, when we observe the light that has visited all these different places, light comes with information from these places. So you don't need to go there, but you need to be able to read information that is stored in the line, mainly using two of the astronomers' tools. One is spectroscopy, and the other one is photometry, spectroscopy and photometry. So we are now in chapter 12 and advancing through evolution of low mass stars. So what's the main point to carry on when we study evolution of stars? Well, if you look around yourself and if you have some basic information about chemistry and physics, you know that your body and the environment we are in is made of little tiny particles named atoms. Now, in the beginning of the universe, in what we call the Big Bang, hydrogen and helium, large percentage of hydrogen and helium that we have in our universe were formed in the Big Bang. So the conditions were just perfect for the formation of hydrogen and helium. So the temperature was just right, the pressure and the density of the gas was just right, and the conditions were such that create the universal abundance of hydrogen and helium, and perhaps some small percentage and trace amounts of other elements like lithium and um, beryllium. But that's it. That's it. So when we think about the other atoms all the way to iron, they were formed inside the stars, in the very core of the stars. So when we study low mass evolution of low mass stars, in fact, what we are really studying is the mechanism by which stars that no longer exist were able to form and to create atoms such as carbon, oxygen, nitrogen that are so abundant in our own planet and so vital for sustain of life. Um, and some other atoms, those that are heavier than nitrogen, were formed when stars that are more massive than the so-called low mass stars we are going to study today, when those stars exploded in phenomena called supernovae, and as a result of this sudden release of energy, these tiny heavy atoms were formed. And sometimes in other astronomers present the hypothesis that are other exotic phenomena out there also able to create heavier or atoms heavier than hydrogen or than iron, I mean. So let's move on and see what's going on here. Let me open my comment bar so I might be able to write something if I need it. There you go. Okay, good enough. So main sequence stars. So when you think about stars, and if you look around and you sample stars in the night sky, um, not those you see, because we know the stars we see. Let me see. The stars we see, they tend to be bright because they are huge. And in fact, in the laboratory, we can learn this type of information that big stars, because they are so huge, we can see them very far away because of the inverse square law. This is one of the um, points we were discussing last week, the inverse square law. So if the star is tiny and small, you don't see the star from very far. But if the star is, what's going on here? Did I miss you guys? Hmm. It's funny, I lost the students. Are you guys still there? Because I don't see you.
Yes, I can see you.
Oh, now I can hear you. I can hear some of you. For some reason, you all disappear. But I can hear somebody there. And um, so if I can hear somebody, oh, there you go. Back. Okay. Very good. Okay. Sorry about that. I thought I had missed you guys. Um, but the inverse square law we were discussing last week indicates that if the star is of a given size, um, the energy the star is producing falls with the square of distance, and somebody observing that star will observe certain amount of radiation, certain amount of energy, and we call that brightness. But imagine we don't just pick stars based on their brightness, but we sample 90%, we sample stars that happen to be in our vicinity. Imagine we can pretty much visit all the stars up to 100 light years away from the sun in all the possible volume around the sun, 100 light years. So if we do that, we are going to find that 90% or more of the stars happen to be stars that are undergoing fusion reactions in their core, like the sun is. When we studied the sun in previous chapters, we learned the sun in the core is producing these fusion reactions where 4 atoms of hydrogen are being fused into 1 atom of helium, and then energy is being produced, and then neutrinos being produced. And the energy gamma rays produced in these fusion reactions is responsible for keeping the sun stable and to provide enough energy to heat up the shells the sun has in its interior part. So the energy that is actually produced in the core is distributed all over, all to the different steps, all the way to the outermost layer of the sun atmosphere. And we find that similar processes also exist in low mass stars other than the sun. And so stars, they are actually fusing hydrogen and producing helium. We find that 90% of the stars in our vicinity, 90% of them, 90% of them are fusing hydrogen into helium. In fact, 4 atoms of hydrogen are being fused into 1 atom of helium plus gamma rays. So gamma rays are being produced plus this elusive particle named neutrinos. And once neutrinos are produced, they just escape the star. So stars, they are actually fusing hydrogen into helium and producing energy, are called main sequence stars. Main sequence stars. And here is the name, main sequence stars. So main sequence stars, in fact, hey Eduardo, how are you? So main sequence stars are 90% of the stars out there. So if you take a scoop of stars in our galaxy, in our Milky Way, especially in the spiral arms, so 90% of them will be main sequence stars. Now, these main sequence stars, how long do they stay? Undergoing these fusion reactions in their very core? So this table 12.2 gives you some hints or some answer to that question. So if you look here, the stars are classified by their spectral type: O, B, A, F, G, K, M. And there is this mnemonic technique to remember this sequence, that it goes from the hotter one, the hot stars, to the cool stars. To the cool stars. Can I write? Let me see if I can write with this. Cool stars. So O, B, A, fine, girl or guy, kiss me is a way to memorize. You go from the hotter one, which is the most massive one too, and then you go to the cooler one that is the less massive. So in this region, evolutionary region we call, or stage in the life of a star, we call main sequence. There is a very common factor connecting all of them. The first one is they are fusing hydrogen into helium. They are stable. They are spending their lifetime, or most of their lifetime, burning and fusing hydrogen, steadily producing helium, and producing and releasing energy that is able to keep the star stable. Without that energy, the star would slowly contract and eventually contract to a singularity we call black hole. Because of that energy, the star stays stable. The star doesn't expand to the point of casting out its external shells, but it doesn't collapse to the point of becoming a singularity. So there is a perfect and stable size of the star, which is determined by the amount of energy that comes from the core, from the central part. But when the star is in this main sequence, in this so-called main sequence phase, there is a very tight correlation between the size, the luminosity, and the mass of the star. So the most massive star are the most luminous and also the biggest star, the one that has the biggest size. But what is interesting is the lifetime of the star is the shortest possible. Whereas the star, there are the smallest one, and is also the skinniest one, and also the less luminous one, the one that produces the least energy, and therefore is the cooler one, the one that has lower surface temperature, is the one that lives the longest in the main sequence. So the time in the main sequence grow like this. So the lifetime in the main sequence grows like this. Lifetime grows like that. From the shorter time to the longest time. Now, very important in this chapter is the introduction of what we call a Hertzsprung-Russell diagram, or a diagram that relates energy produced by the star, sometimes luminosity, sometimes absolute magnitude, and surface temperature or spectral type. It doesn't matter. And what this diagram shows is the star change its position as in this diagram as the star itself evolves. Now, when we study this diagram, which is called Hertzsprung-Russell, let me see if I can write here, Hertz, sprung, Russell. Let me see if I can write. That's Hertz with Z. Hertzsprung-Russell diagram. So they were two astronomers that independently got to the same conclusion. And this diagram again relates luminosity, which goes from the least luminous to the most luminous stars up there, and from the hottest one in its surface temperature to the coolest one right here. So the sun is presented right here in the middle, about 6,000 Kelvin. That star has one solar luminosity. And what we found when we study stars, once they are formed, once they come out of their protostellar phase, which we studied in previous classes, and the star keeps contracting. As the star contracts, the luminosity, the brightness of them diminishes, as you can see in this track for stars with luminosity or with mass less than our sun. Their luminosity, as they evolve, diminish in this track up to the point they becomes what we call main sequence. So this HR diagram and what you're seeing, these lines on the upper right hand side and above the main sequence, these tracks are theoretical tracks that follow the star since the moment the star itself is able to be observed and visible by astronomers. And as the star slowly contracts and diminishes its volume, the luminosity of them diminishes too, the surface temperature slightly increases to the point that eventually the core is going to be hot enough to ignite and initiate fusion reactions. And when that moment is achieved, the star is classified as a main sequence. So the steps that exist before the main sequence phase are called pre-main sequence phase. So stars whose tracks are indicated in this diagram here are called pre-main sequence, not main sequence, they are pre-main sequence phase. And what is being indicated are sequence of steps in the stellar evolution prior to the moment they become a main sequence. They become a stable star like our sun, where fusion reactions are taking place in their very core. So here is kind of a ratio. Let me go through this diagram with you. So in the y-axis, it is shown the percentage of mass. The percentage of mass when the sun was formed, and 0, 20, 40, 60, 80, 100 indicates percentage, right? So let's say what I'm reading here is there is 25%, in fact about 30% of helium when the sun was formed, and 70% of hydrogen when the sun was formed. So it gives a total 100%. This is not exactly true because the sun had primarily hydrogen and primarily helium, but there was also trace elements of all the other atoms and when the sun was formed. But throughout the star itself, the abundance of the sun matched the abundance of the material in the interstellar medium. Okay? But as the sun evolved, and since 4.5 billion years ago, if we could take a scope of the solar interior, what we would find is that in the very central part right here, so the x-axis is talking more about the distance from the surface all the way to the core. What we find is that very close to the core, 60% or 70% of the material in there is helium. So hydrogen has been converted into helium as the sun has undergoing and sustained this process for about 4.5 billion years. For 4.5 billion years, the sun has continuously fused hydrogen and helium to the point that nowadays the core is getting primarily a core of helium. So it's going to take another 3 billion years before the core itself gets completely filled with helium, in which case changes will occur to the solar interior. So when we talk about stellar evolution, we are talking about the process by which the production of energy in the solar core changes, because the fuel that is pumping up this fusion reaction, which is hydrogen is over in the core. So hydrogen is not going to be finished in the surface. It's not going to be finished in the shell on top of the core, but in the core itself, the hydrogen will be depleted, and its ashes, the ashes of these fusion reactions, will be primarily helium atoms. Okay. When hydrogen fusion in the core stops. Okay. So what's happening with hydrogen fusion stops? Well, hydrogen fusion can go on as long as you have hydrogen. But eventually, hydrogen in the core is going to be depleted, completely changed into helium atoms. So when this process occurs, what we learn is, and according to theories and calculations, what they show is that once the fusion reactions in the core is gone, the core starts slowly contracting and heats up. And then the outer shell, the shell surrounding the core, start fusion reactions of hydrogen into helium. So you have a helium fusion shell surrounding the core. So the fusion reactions is not in the core anymore. The core is contracting, but the shell surrounding the core undergo fusion reactions. Now, the fusion reactions release energy in the shell surrounding the core, and this energy is good enough, is efficient enough to expand the outer shells. So now the sun undergo an imbalance of energy. So if you take a shell in a solar interior, there is an imbalance. So the shell is still supporting gravity force, the weight of the star above it. But the energy that is being released from the core is big enough to overcome the weight of the star, and as a result of that, as a result of this imbalance of force, you think you have a certain amount of pounds pulling inward, and you have a much bigger amount of pounds pushing outward. The result is the outer planes, the outer layers of the sun at that phase expands. So when the fusion reactions in the core are halted or stopped, the core contracts and heats up, and the outer shells expands, and as a result of this expansion, the separation between molecules and atoms diminish, and then the gas gets cooler. So we have a cooler gas in the outer layers. Now, cooler gas in physics and astronomy, like we saw in chapter 4, translates into redder color. So the star expands, cools down in its surface area, and becomes redder. And we call this phase the phase of a red giant. Red giant. Red giant. It's funny, I'm not able to write well with this. Red. It's really not writing well. Don't know why. Okay, when hydrogen fusion in the core stops, its temperature, the temperature in the core increases. This is true. This is true, and its thermal pressure increases too. So this is good. So the size of the core, that doesn't make sense. Wait a second. When hydrogen fusion in the core stops, okay, its temperature, which the temperature of the core increases because the core contracts. So B is good, D is good. So A and C are not good. And its thermal pressure. So as the temperature diminishes, the pressure in the core, the outer pressure increases, and the size of the core is diminishing. I don't have an option here, so this is funny. The core is diminishing, the pressure is increasing, the temperature is increasing too. Yeah, so I don't have a correct answer there. Sorry about that. I will take this question out. Let's just tackle the red giant phase, and let's see if we can follow this this illustration here. The resolution is not good. I can't barely read that. So, but we don't need to read this fine print here, but here's the example. You have a star um, with a core, about 25%, 25% of the stellar interior. You have the fusion, the radiative diffusive shell right there, and the convective zone, as we saw previously. So eventually, when the core, this lighter part of this in the figure, when the core becomes depleted of hydrogen, because hydrogen has been all used up to form helium, when this happens, now the core starts slowly contracting and heating up. And then the outer layer of the star expands and cools down. Now, what is being said here is when for a star that has more mass and therefore has more gravity, and in next chapter, we are going to tackle the high mass star. So how high mass stars, since they have more pressure on the core, because the stars are heavier, then this fusion, this rate in which energy is produced goes much faster. And that's why massive stars, they don't live longer. They die out quickly because the rate in which energy is produced is speed up, is accelerated because of this high pressure that exists in the core. That's a main sequence star with the core, fusion, hydrogen, and helium. That is where fusion reaction is taking place. And you have a known burning envelope where energy produced in the core finds its way to the surface and eventually escape. Now, in the red giant star, in the red giant phase, something different happened with the star. And what happens is the core is now undergoing contraction and heats up. Heats up because the size of the core diminishes as a result of the lack of fusion reactions that is taking place in the core. But there is a shell here, hydrogen burning shell. There is a shell that burns around the core itself. So the shell undergo fusion reactions not in the core but in the shell. So as a result of this, and if the calculation is done properly, and astronomers and physicists have made that, they find the energy that comes out of this system, core and fusion shell, are such that this energy is able to push the outer layer out, to expand the star. And again, as the star expands and cools down, and we call this phase the red giant phase. As the star cools down, it gets redder in coloration. What causes a low mass star like the Sun to evolve away from the main sequence? What causes is hydrogen is exhausting the core. This looks good. All hydrogen becoming helium. No, it's not all. It's not all over the star. It's just in the core, and there has nothing to do with the carbon fusion yet. So, and now the star is in the red giant, and the star is a big one, kind of a cool and red. So what happened? Well, the core keep on contracting. See, the core is contracting, and when you contract the gas, you force the gas into collision. So the elements that make up the plasma or the gas are forced to packed in a smaller volume. And the resultant effect in nature is there will be more collisions going on, temperature goes up. And what we learn is that eventually when the temperature is 100 million Kelvin, that temperature is good enough to initiate helium fusion reactions. Helium fusion reaction. I can't write well with my stylus. The stylus is writing terribly. I don't understand why. I have to check and see what it is. So helium fusion reactions, I apologize for that. So helium fusion reactions is gone. In fact, it initiates in the core because the core now is hot enough to initiate the fusion of helium into carbon and oxygen. So now the star passes the giant phase, is not in the giant phase anymore, but is in the phase where the fusion reactions in the core are back into consideration. But it's not hydrogen into helium, but it's helium in carbon and oxygen. It's called triple alpha process. And this starts all of a sudden in a phenomenon we call helium flash. Helium flash. Now here in the diagram, this is more or less displayed where you have a star that is in the main sequence. Let's say it has a certain luminosity, a certain amount of energy coming out of it, and a certain surface temperature. And the star expands and becomes a giant when the core has no hydrogen anymore to keep on fusing into helium. But eventually, the core starts contracting, and the star eventually becomes stable enough, and then fusion reactions takes place in the core, where helium is fused into carbon and oxygen. So when that moment arrives in the lifetime of a star, we call this star a horizontal branch star. So a horizontal branch star is one that fusion reactions are again taking place in the core. But it's not hydrogen, it's helium into carbon and oxygen. So as it happened previously, eventually this carbon is going to be gone. In fact, the helium is going to be gone. The core is going to be a core of carbon atoms only. And then these fusion reactions will stop. And then again, the core will start contracting and heats up. And there will be a fusion reactions surrounding the core, hydrogen and helium, both of them together. And then the star expands to what we call asymptotic giant branch. So the star grows to be as big as 100 times bigger than the sun, and so much energy comes from the core that most of the outer layer of the star is expelled back in the interstellar medium, and we call that planetary nebula. Planetary nebula. So those are the steps, and Lyra has such a planetary nebula named Ring Nebula, and those are the primary steps in stellar evolution. Okay. So for a low mass star, what do you need to know? Well, low mass, a star in general starts its life by allowing gravity to bring gas and to bring this gas to a central part where the star is going to be residing. So once the star is in place, so what happened? Well, now I have a star, but eventually the core will be such that we'll be able to initiate fusion reactions of hydrogen into helium. And when this moment starts, the star becomes a stable star. So it doesn't expand, doesn't contract, and stay most of its lifetime as a main sequence. Well, but after, let's say, 80% or 9% of its lifetime, the hydrogen in the core is going to be depleted, right? Now we have a core of helium. So what happened with the star? The core contracts, outer layer expands, and the shell, the outer shell cools down. This star becomes red, and we call that phase a red giant star. Well, but the core keeps contracting, and eventually we'll reach a temperature that is good enough to ignite fusion reactions of helium. Now helium, once initiates fusion reactions, the star again becomes sort of what was in the main sequence, had a fusion reactions in the core, except it's not hydrogen, it's helium. So once the star has reached that phase, we call horizontal branch star. And the star will stay there for quite short amount of time, and then eventually helium will be completely turned into carbon, and again the core will start to contract again, outer layer expands, the star becomes a symptotic giant branch star, and eventually these outer layers are cast off from the star, and we call that phase planetary nebula. And when that phase reaches, the core of the star is the only one that remains alive, and we call that a white dwarf. A white dwarf. So a white dwarf is a degenerated core of a star, a low mass star, that is there surviving and has some thermal energy, but in no time that's going to go away, and the star becomes a dark dwarf. White dwarf is made of matter so much compact that that you don't have an equivalent here on planet Earth. Okay, so white dwarfs can't be big stars; they can't be more than 1.4 solar mass, or they explode in supernova type 1, as we will learn next class. Okay. So those steps are the important steps in stellar evolution I would like to bring to your attention, and especially with the introduction of Hertzsprung-Russell diagram, the diagram that relates luminosity and temperature or spectral type in stars in general. And when we talk about stellar evolution, we are talking about the changes in the ratio of these two parameters, luminosity and surface temperature. So the star doesn't move in space. The star stays in the same space, but they expand, contract, change color, change surface temperature as a result and in response to the changes that occur in their very core. Okie dokie. Any question you want to ask? All good? Okay, let me stop taping and then I can talk to you. Okay, good night, you all.